Hey there, welcome to this presentation on all pairs shortest paths with few weights per node. This is a paper together with my amazing co-authors Amir Abboud, Sujin, Virginia Vasilevska-Williams, and Zui Ji. My name is Nick Fischer. So let's get started. This work is about the all pairs shortest path problem, for short APSP, which is arguably one of the most fundamental graph problems out there. So the input consists of a directed edge-weighted graph, say on n vertices, and the goal is to compute all pairs of distances in this graph, or in other words, to compute the full distance matrix, which I want to denote by D throughout this talk. Now, APSP is not only super fundamental for graph problems, but it is also one of the core problems in fine-grained complexity. In fact, one of the three main hypotheses in fine-grained complexity is that APSP cannot be solved in truly subcubic time. So there's no algorithm in time, n to the 3 minus epsilon for positive epsilon. So this hypothesis has been used to prove a lot of cool lower bounds for a lot of problems which seem super unrelated to APSP. But this will not be the focus of this talk. Instead, I want to ask the question, which instances of APSP can be solved in truly subcubic time? Turns out there was a lot of work on this. So a simple example would be sparse graphs, which clearly can be solved in, a tilde of mn, where m is the number of edges. So this is by just running Dijkstra's algorithm from every node. So this clearly runs in truly subcubic time as long as the number of edges is truly subquadratic. But there's more. Let's say undirected unweighted graphs. Since 30 years now, it's known that with Seidel's algorithm, you can solve such instances in time into the omega, where into the omega is the exponent of matrix multiplication. So yeah, to allow for like a nicer way of citing all these algorithms, let me just assume from now on that omega is equal to 2. So Seidel's algorithm would run in n squared time. Really, this is not necessary to assume for any of these results. It's just that otherwise you have all these ugly constants depending on the current best bounds for omega floating around. And this way it's much easier to compare. Okay, so it turns out undirected graphs can also be solved in truly subcubic time as long as they have small weights. So specifically, that's its algorithm in time n squared times w, whenever the weights are from a range, of weights at most w. So this is truly subcubic as long as w is truly sublinear. Directed graphs turn out to be a little bit harder, but still subcubic. For instance, Zwick's algorithm runs in time n to the 2.5 for directed unweighted graphs. And again, this can be extended to small weights with this running time, which, as you can verify, is also truly subcubic as long as w is truly sublinear. Here's a very different class. What about node-weighted graphs? Okay, so instead of edge weights, now the nodes have weights, and as you could, as it's natural, now the weight of a path is the sum over its node weights instead of its edge weights. So Chan in 2007 proved that you can actually solve this APSP instance in time n to the 2.75. So it seems even a little bit harder than directed unweighted APSP. 2 years later, Justa improved this algorithm depending on the current best bounds of omega, so it's not reflected in this running time. Okay, so in our paper, we provide two main results. The first one is an improvement of this algorithm to n to the 2.5. So basically, we show that this can be solved as fast as directed unweighted graphs. So as fast, at least as if omega is equal to 2. Okay, but this is sort of a very natural and cute algorithm. We'll mostly talk about this in the rest of this talk, but I want to emphasize that actually the sort of deeper contribution of our paper is not about node-weighted APSP, but about the next problem. So consider this instance of APSP. It's directed edge-weighted graphs again, but with the restriction that every node is incident to at most d distinct edge weights. So say the set of outgoing edges is at most d distinct weights. This is a very interesting instance because it generalizes all of these previous instances. Let's quickly verify. Okay, node-weighted APSP is really just the special case where d is equal to 1, right? Because if you have, if each node has only, like all the outgoing edges of a node have the same weight, you might as well pull that weight onto the node and view it as a node-weighted graph. Okay, it's clearly harder than directed unweighted graphs. And well, if you have directed graphs with small edge weights of, value at most W, then clearly this is an instance of the problem with D equals W. And well, this is just strictly harder than for undirected graphs. And even for sparse graphs, you can sort of view this as a generalization by maybe, relaxing this requirement to not be that all nodes have at most D distinct weights, but let's say the average number of distinct weights per node is at most D. Okay, now what's known for this? In 2009, Juster proved that you can solve it in this running time. So basically he extended his algorithm for node-weighted APSP to this running time and to the 2.75 times root D, which actually runs in truly subcubic time as long as D is less than root N. Okay, so that's cool, but it looks slightly off because, well, if you compare it to these previous running times, those actually run in truly subcubic time as long as W is truly sublinear. So there seems to be a gap here. In other words, it was open before our work if the root n, like APSP with at most root n distinct weights, can actually be solved in truly subcubic time. Now we answer this question and we prove that, for basically the whole range of Ds, as long as D is truly sublinear, we do get truly subcubic time algorithms for APSP. That's, of course, the best you could hope for, at least if you believe in the APSP hypothesis, because if you set D equals N, then this restriction is void and you just have the general APSP problem, which of course should not be solvable in truly subcubic time. Right. Okay, so let's, for the rest of the talk, I will talk about mostly about the node-weighted algorithm, which runs in n to the 2.5, and then I'll give some pointers about this final one. But let's get started with node-weighted APSP. So just as a quick recap, right? Node-weighted APSP is this problem. You're given a directed node-weighted graph. The goal is still to compute the distance matrix. Now, just to get some details straight, whenever I say the weight of a path, let's say this one, this would be the shortest path between this node and that node. This actually has weight 9, we say, because we disregard, let's say, the node weight of the starting vertex, just so that, distances from, like, the distance from every node to itself remains 0. But really, this is just a technicality. Okay, so the main result we prove is node-weighted APSP can be solved in time n to the 3 plus omega half, which, this I've said before, is n to the 2.5 if omega turns out to be 2. Before I can talk about this algorithm, we first need to talk about some basics. So here's a very basic definition in this context, which is the min-plus product of two matrices. This is sort of a special matrix product, which is super relevant for distance type problems. Okay, so let's say A and B are matrices, then their min-plus product, which will denote by this star, is another matrix where each entry ij is defined with this equation. So for instance, this value 6 would be essentially the inner product of some column and some row. But instead of taking the normal inner product, you now sum up all pairs of numbers, let's say 14 plus 9, but then in the end you take the minimum over all of those. So in this case, the minimum would be 0 plus 6. Okay, why is this super relevant? Well, let me introduce one more piece of notation. Let's say DH, D at most H is the H hop distance matrix. Okay, so it's not necessarily the shortest path here, but it is the length of the shortest path, which uses at most H hops. Then there's this super well-known factor. Actually, it's an easy observation that the H hop distance matrix can just be obtained as the H-fold min plus product of the one hop distance matrices. And now the one hop distance matrix, this is essentially the adjacency matrix of the graph, where for every edge you put the weight, for every non-edge you put infinity, and for every diagonal entry you put 0. Okay, so for instance, by setting H to be n, then it turns out we can get access to the full distance matrix just by taking like an n-fold min plus product. And from this, you can also derive an algorithm for APSP, namely by just evaluating this right-hand side here, either by, the naive way would be to do it by computing n min plus products, but Turns out this is associative, so you can evaluate this expression with repeated squaring. In this case, you get an algorithm which is basically the same running time as min plus products, which shows that APSP, like min plus product, cannot be computed in less than cubic time, as otherwise there would also be a truly subcubic algorithm for APSP then. Okay. This is just basically to settle the notation. Now, let me talk about the previous algorithm for node-weighted APSP, 2 to Chan. So it's based on two main ideas, which we'll talk about separately. So the first idea is that even though general min plus products cannot be solved faster than cubic time, there are some structured min plus product instances which can be computed in, subcubic time. Specifically for node-weighted graphs, you can always evaluate the min plus products of a one-hop matrix with an arbitrary matrix A, or the other way around in time n to the 2.5. If you think about it, I don't want to talk about this in detail. I just want to give you the key observation here, which is actually very simple. This would be the one-hop distance from the graph we've seen before. And well, if it's a simple observation that in every column, all non-trivial entries are always equal, right? Because this is really just the distances from some node to another node. Maybe this would be rows, I'm not sure. Anyways, so really, all these distances are equal to the node weight. So, because of the structure, actually, it turns out that you can devise this algorithm runs time into the 2.5. So, okay, that looks super promising, right? Because now maybe we want to evaluate this expression using this faster algorithm for computing min plus products. But of course, if you want to make use of this fact, you would have to evaluate it, let's say left to right or right to left, whatever, which would amount to computing n such products, which runs the time n to the 3.5. And that's, of course, terrible. So that's not the way to go. But the idea is still, it's a good idea. Let's keep it in mind. Here's the second idea. The problem really would only be if the hop length of a path is too long, because then really this computation from before is too expensive. So maybe we should shortcut long paths. So specifically, let's say this is our graph. We will sample a set of pivot nodes, which I want to denote by S, and let's visualize it by these yellow squares. They're supposed to hit all shortest paths of hop length at least h. Okay, in this case, I claim that we get the following identity. It's a mouthful, but we'll go through it slowly. Okay, so I claim that the distance matrix D, the proper distances, can be obtained as the coordinatized minimum of two matrices. First of all, the h hop distances, and then this sort of complicated matrix product. Okay, let's go through it. Really, there's only two cases. A shortest path between two nodes either has hop length at most h. And in this case, clearly it's just like its length is reflected in this matrix, in the h hop distance matrix. Or the shortest path between two nodes has hop length more than h. But then what is going to happen? We sampled some random pivot nodes. So with high probability, we are going to hit the length h prefix and the length h suffix of our path with two pivots. Okay, and so in particular, the path can be decomposed as a path of hop length at most h from our current node to a pivot, followed by a potentially long path from a pivot to another pivot, followed by a trailing length h sequence. Okay, so this intermediate path between the two pivots is not hop restricted anymore, but well, it goes from pivot to another pivot. Okay, so how can we make use of this? So if these are the two ideas from before, right? Now I claim we really just want to evaluate this identity in a smart way, exploiting that a lot of these min plus products in the expression are actually structured. So let's try to do this. Well, first of all, we can always compute the distances from all pivots to all other pivots by, let's say, by one call of Dijkstra's algorithm for every pivot. Then we get this running time, size of S times n squared. Then what remains is to compute all these min plus products, and I claim that we can evaluate all these min plus products in this running time, h times n to the 2.5. Let's verify this. So just computing the h-hop distance matrix clearly amounts to h min plus products with the one-hop distance matrix, runs in time, h times n to the 2.5. And what about those? Those are the same thing, right? You just multiply from the left or multiply from the right with this distance matrix by using idea 1, in this case 2h times, we have another contribution of h times n to the 2.5. Okay, now clearly, okay, recall from before that S has size n by h. So we get this trade-off of n cubed by h plus h times n to the 2.5, which balances out at n to the 2.75. Okay, and this really is Chun's algorithm. Now, in order to get to our improved n to the 2.5 algorithm, I will talk about both ideas again and tell you how to slightly improve these ideas. Turns out, actually, both these improvements are sort of known. So we didn't really need like radically new ideas here. We just had to put it together in the right way. So the first improved idea is to not only consider square min plus products, but to also consider structured rectangular min plus products. Okay, so recall that this min plus product of the one-hop distance matrix with an arbitrary matrix A is always computable in n to the 2.5 time. But turns out if they have very asymmetric sizes, so let's say our one-hop distance matrix is actually n by n, but this matrix A is a rectangular matrix of size n times s, then we can compute this min plus product even faster, namely in time s times n to the 1.5 plus n squared. Again, I'm always assuming omega is equal to 2 here. Okay, so what does this running time mean? Well, n squared is just necessary to read the input size of the D, like the one-hop distance matrix. This other running time here, s times n to the 1.5, indeed becomes n to the 2.5 if s is n, so first in the square case, but it is much better for rectangular matrices. And in the same way, you also get this result for multiplying the other way around. Okay, again, is this useful? Let's see. Recall that this was our equation, our identity from before. And turns out, well, if you try to evaluate this now in a careful way, exploiting that we have a lot of rectangular products, actually, this is not immediately helpful. I mean, already, like just to compute the first contribution, like the first matrix, the h-hop distance here, we cannot make use of rectangular products at all, right? But it's still it's an interesting observation, and this was, for instance, what Justa used in his algorithm to obtain speedups based on the currently best rectangular matrix multiplication exponent. Okay, but we're going to use it in a slightly different way. Namely, consider the following relaxation of the problem. Suppose that we only want to compute the distances between some target nodes t. So the distance matrix restricted to the nodes from t in t to t. Then there's an easy way to replace this identity. It'll look scary again, but it's really just the same identity where now we have restricted all matrices to only concern the vertices in t. Okay. Now this expression can actually be evaluated in a smarter way using rectangular min plus products. Specifically, this is the observation. If we know the S to S distances, then we can compute the T to T distances in this running time. Okay, let's verify. So this is the running time of H min plus products, like H invocations of this improved idea 1. Let's see. To compute this, the H-hop distances from T to T, well, clearly we can just evaluate these, call idea 1 H times. And with each invocation, the matrix A has at most T columns or rows. So actually this runs in time H times size of T times n to the 1.5 plus H times n squared. Okay, that's cool. What about the more complicated right-hand side of the minimum? Well, here, first of all, we already assume that we know the S to S distances, so we do not have to compute them. Instead, what we'll do now is we will multiply this matrix from the left and this matrix from the right. Or even more explicitly, we'll always multiply like the individual one-hop matrices from the left. And then finally, we will take this entire matrix here, which will now be an arbitrary matrix, and multiply it from the left to all of those matrices. Now, each such min plus product either has a small dimension of size t or it has a small dimension of size s. So yeah, in both cases, we get an algorithm. We can invoke this improved idea from before with s being equal to the size of s or the size of t. So we derive at this running time. Okay, so let me summarize. This idea seems to be useful when we're not interested in all distances, but only a subset of the distances. So how should we improve the second idea? Recall that the second idea was to sample some pivot nodes which shortcut some distances in the graph. And now, okay, the second improved idea is really basic and has been around in a lot of works, which is multi-level pivots. So instead of just sampling a single set of pivots, we will sample, let's say, log n levels, or maybe slightly less, but pivot sets S0 to SL, where each such set has size n divided by 2 to the L and is supposed to hit shortest path of length roughly 2 to the L. Also, let me assume that the first set of pivots is equal to the full node set. Now, really, this idea has been around for a long time. I'm just citing Zwick here because our specific implementation of this idea is just so similar to his algorithm for directed unweighted APSP. Let me give you a picture. So how does it look like? Well, in our graph, basically all nodes become level 0 pivots. Then roughly half of the nodes will be level 1 pivots, roughly a quarter level 2, and so on. Until at the final level SL, only like a 2 to the L fraction of the nodes remain such pivot. Okay, now how do we put these two ideas together? It turns out it's actually extremely simple. Recall this was our observation from before. And then consider this algorithm. Well, okay, we can compute the SL to SL distances just by Dijkstra's algorithm. Right, as before, we do this in the base case. But then instead of just picking a single level of pivots, we will like enumerate over all of our levels, starting curiously at the top level, like from top to bottom, instead of what is, I guess, more like at least what happens in Zwick's algorithm, which would be like from bottom to top. And in each step, we compute the SL distances from the SL plus 1 distances, just by the observation. So clearly this algorithm is correct. And in the end, we can return the proper distances as the S0 to S0 distances, just because those happen to be all nodes. So let's have a look at the running time. Okay, so the first step runs in time SL times n squared, where SL, like for each top level pivot, we run Dijkstra. Okay, the loop actually doesn't account for much because they really are just at most a logarithmic number of iterations. And each iteration runs in this running time now. Okay, it's again sort of complicated, but really all I've done is plugged in the parameters into the observation. So here recall that SL was a set of shortcuts which was supposed to shortcut paths of length at least 2 to the L, so H is 2 to the L. Okay, S and T are now SL plus 1 and SL. Okay, and if you think about this, well, first of all, we said each such set SL has size at most n by 2 to the L. So the first contribution here is n cubed by 2 to the capital L. Now, similarly, this expression here, the inner parentheses becomes n divided by 2 to the L, 2 to the small L. So really this 2 to the small L cancels, and this becomes n to the 2.5. Except for, well, this remaining term of the form 2 to the L times n squared, which is maximized at 2 to the capital L. Okay, so we really achieve this running time, which is clearly optimized at n to the 2.5 by choosing L to be half log n. Okay, so yeah, hopefully this convinced you that node-weighted APSP is an n to the 2.5 time, and that the algorithm is actually pretty simple and natural, I'd say. Some optimizations. Let me just remark some. So first of all, the running time can be improved like if now we're not thinking about omega equals 2, but for the current best bounds in omega, it can actually be improved to be slightly better than n to the 3 plus omega half. So specifically, we get this numerical value of n to the 2.667. If you additionally, instead of just using rectangular min plus matrix multiplication, you're also willing to use rectangular standard matrix multiplication and some more tricks. What I said before is randomized, but this idea based on these multi-level pivots can be de-randomized in exactly the same way that Zwick's algorithm for directed unweighted APSP is de-randomized using so-called bridging sets. It's a little bit more subtle because, in this original algorithm, the construction was bottom to top, whereas ours is top to bottom, but it still works. Finally, what about negative and or real weights? Turns out the algorithm can be easily modified to also work with those. Really the only step where this distinction is important is when you call Dijkstra's algorithm, because this might not work for, let's say, negative weights. But this is easy to replace by another algorithm. Okay, so that's all I wanted to say about the algorithm to node-weighted APSP, but let me quickly comment on whether this running time n to the 2.5 is actually plausible to be best possible. So yeah, let me compare directed APSP with, node-weighted APSP with directed unweighted APSP. Recall that this was, this problem which by Zwick's algorithm is in time n to the 2.5. Now here's a trivial observation. Really, if directed node-weighted APSP is in time faster than n to 2.5, then so is directed unweighted APSP. Clearly, right? You just put, I don't know, weight 1 on every node or something, so that you just get rid of the weights. So that this is not saying anything. What is a little bit interesting is that you can also extend this lower bound to work for undirected graphs. So the lower bound is if undirected node-weighted APSP is in time n to the 2.5, then directed unweighted APSP is in time n to the faster than n to the 2.5. At least assuming if omega is equal to 2, otherwise, you have to, those lower bounds depend on omega and get slightly worse. Okay, I'll just give you like a very quick proof sketch. So turns out, by previous work due to Chan, Wasileska, Williams, and Zhu, it's known that the following graphs are provably the worst case instances of directed unweighted APSP. So, okay, those graphs look as follows. You have n nodes on the left and n nodes on the right. Really, you only care about the distances from the left to the right. And in the middle, you have root n paths of length root n. And now what all these nodes on the left do is they have outgoing edges. In fact, only one outgoing edge to one outgoing edge to every path. And on the right, you have only one incoming edge per path. Okay, so all I want to show you is, turns out that this particular instance can be easily translated into an undirected node-weighted graph by the following, simple transformation. Let's make all the edges undirected. This causes some problems, of course, because now perhaps you wanted, like in your path, you could jump between the left and the middle part of this graph a couple of times before you move to the right. So in order to prevent this, we just put node weights here. Namely, we put some small node weight, let's say 1 on all the middle nodes, and we put some very large weight, let's say n on all the left and right nodes. So now it never makes sense to jump from the middle to the left, because this is always more expensive than just following an arbitrary path to the right. Okay, great. So I finally want to talk about our algorithm for few weights APSP, which let me call the problem D weights APSP. Here's quickly again the definition. So the input is a directed graph where all nodes have at most D distinct outgoing edge weights. So for instance, in this graph, I don't know, the D would be 2 because actually you can verify that all nodes have at most 2 distinct outgoing edge weights. The goal, as before, is to compute the distance matrix. Now, our second main result is that D weights APSP can be solved in truly subcubic time whenever D satisfies this constraint, when D is less than n to the 3 minus omega, which, if omega is 2, again becomes truly sublinear. Okay, here's a very quick overview of the algorithm. If you're interested in a more detailed presentation of this, actually, I presented this in the ETH Algorithms and Complexity seminar a while back. This talk is somewhere on YouTube if you're interested. Okay, so but let's just jump through the steps sort of quickly. What do we do? First of all, the first step is sort of standard and fine-grained complexity. Instead of thinking about d-weights APSP directly, it is much more convenient to think about a certain triangle version of the problem. In this case, this would be like a d-weights exact triangle instance. Okay, what does this mean? We reduce to a tripartite graph where now the goal is to reduce is to detect triangles of total weight 0. Like for instance, this triangle here, it has total weight, total edge weight 0. D-weights as before means that now the set of outgoing edge weights for each node is small, it has size at most d. So this step is basically only out of convenience. And then we have two highly technical and complicated steps. The first one is we do a weight uniformization, which means that we transform the graph in such a way that there's not only at most d distinct weights per node, but there's in fact at most d distinct weights globally. So now all the edge weights in the entire graph share the same weights, and there's at most d distinct such weights. Then we do another extremely technical step, the weight regularization, which is to transform the graph further to ensure that every weight does not appear too often. In fact, we make sure that at every node, each weight appears at most n by d times, which is, the expected number of times. Okay, and then in this highly, uniform and regular graph now, oh, sorry. Yeah, what does it mean to be regular? Again, like for every weight and every node, there's at most n over d outgoing such edges. Then the third step, and maybe the most surprising step, is in this preprocessed graph now, you can use additive combinatorics. So specifically, you can use the BSG theorem from additive combinatorics to make sure that the set of weights, which let's denote it by A, is not arbitrary, but is actually highly structured. Specifically, it has small doubling, which means that the sum set of the set with itself, denoted by A plus A, this is a set which consists of all pairwise sums of elements in the set A. This is actually pretty small. And then you can combine this with algebraic algorithms, specifically based on matrix multiplication and sparse polynomial multiplication to run in this running time. Okay, if you work out the details, you indeed arrive at our theorem here. As I said before, I won't go into more details. Feel free to check out that other talk if you prefer. Let me conclude with some open problems. So first of all, can we improve the running time for d-weights APSP? So what I said before is correct. Like there is, like for every sublinear d, there is an algorithm which runs in time, in truly subcubic time. But we do not achieve an algorithm of this nice form, like of n to the 2.99 times d to the 0.01, let's say. If you could verify a running time of this would imply the same statement, but we do not achieve such a nice running time. The reason is that this weight regularization step just turns out to be so technical. We have some very complicated recursion going on in there, which actually blows up the dependence of these hidden constants here to be much worse than what you would expect. So yeah, the open question would be, can you achieve such a nice looking running time, or perhaps even n to the 2.5 times root d? This would really match the known algorithms for directed or unweighted directed APSP with weights from a small range. Yeah, second question is, can you prove more equivalence between APSP variants? For instance, we designed an upper bound for node-weighted APSP, which is n to the 2.5. But can you actually prove that this is equivalent to some other n to the 2.5 time problems? There's, in fact, a lot more matrix problems out there which have this intermediate complexity of n to the 2.5. Maybe some of those are equivalent. Finally, and this is perhaps the toughest open question here. Can you use these ideas to possibly design a universe reduction for APSP? meaning a reduction from general graphs with edge weights to graphs where the edge weights are in this range 1 to n. Recall that this was not break the APSP hypothesis, because even like for those APSP instances where the weights are from 1 to n, we don't know any subcubic algorithm. But it would sort of tell us that the hardest instances of APSP are exactly those where the weights are small. This is highly unclear. It might also be that this just doesn't exist. Okay, anyways, thanks for listening.